All right. Yep. Oh. I can't do that because some people have scheduled classes. It wouldn't be fair if they have class. Yeah. All right. So I had a few people talking to me during lab yesterday and via email and just in the hallway saying, like, this is really challenging, like conceptually very difficult. That's okay. The biggest and best way you can improve your understanding of NMR is by doing practice problems, and that's what we're going to do all day today. So let's take a look at problem part A of the pod. What reagent do we need to oxidize an alcohol to a ketone? PCC. You can use PCC or chromic acid. Either one works, right? So just review of old chemistry. Now what we've got to do is we've got to look at our product and identify unique sets of protons, right? So let's go over here. I've got a proton coming off of this position. Let me change the thickness here. Got a proton coming off of that carbon. Are there any others like it? Yeah, the other three methyl groups coming off of that carbon, or the other three protons coming off of that methyl group are all equivalent, right? Are there any other protons that are equivalent to those?
Yes. The other methyl.
Yeah, the other methyl, right? So if we look at this isopropyl group, we could say that this isopropyl group can spin around like a helicopter blade, right? Because that sigma bond can rotate. So they're essentially occupying the same space on the NMR timescale. So all of the red protons will be equivalent. What about this guy? Are there any others like it? No. So that's unique. What about this proton? Are there any others like it? Yeah, the one that's attached to that same carbon. These are called enantiotopic protons. There's not one that's cis to any other functional group. There's no stereochemistry, so they're enantiotopic. They share the same chemical shift. All right, the next one that we have comes off of here and here. And are these the same or different? The same. A few people were asking me, they were saying, well, this one up here, it's closer to the oxygen, so why isn't it in its own chemical environment? It can spin, right? So that ketone that's coming off of the benzene ring will spin around, and it has equal probability of being on either side, right? So in this case, they both share that same chemical environment. So we'll label that as H, and then let me come up with a different color. And we've got these protons over here. All right, so now what I typically like to do is I like to make a table where I've got my proton here, I've got my integration, I've got my multiplicity, and I've got my chemical shift. Whoops. And we'll just make a simple table. And I'll start out with the red proton, the blue proton, the green protons, the black protons, and the orange protons. Okay, the red protons. If we think about the integration, how many red protons make up that signal? 6. So we would just say it has an integration ratio of 6. If we think about the blue one, how many protons account for that signal? 1. So if we think about the signal we'll see for the red protons versus the blue protons, the red protons will be an area 6 times greater than the area for the blue signal, right? What about green? 2. We have 2 green protons. Black, we have 2 black protons. Orange, we have 2. All right, now we go into the multiplicity column. All right, let's start again at the red one. When determining multiplicity or splitting pattern, what's the first thing we look for? 2 or 3 bond neighbors. We can't be split by equivalent protons. So in this case, a red proton won't split another red proton. Are there any 3 bond neighbors? Yeah, the blue proton is a 3 bond neighbor to the red proton. So we have 1 3 bond neighbor. What will the signal be split as? A doublet, right? So the H that's red, not doubt, doublet, it will be split into a doublet because we have 1 blue proton splitting it. All right, now let's think about the blue proton. How many 3-bond neighbors does it have? 6 total 3-bond neighbors to that blue proton. Why don't we count the green protons? Because there's 4 bonds separating them, right? So if we count sigma bonds, those green protons are 4 sigma bonds away. We don't count them. So the red protons are 3-bond neighbors. We've got 6 of them. What will the splitting be? A septet. Okay? Which is a signal splitting of 7 if you're not familiar with that prefix. All right, what about the green protons? How many 3-bond neighbors? None. Trick question, right? There are no 3-bond neighbors to those green protons, so what will the signal appear as? Singlet. It'll be unsplit. All right, what about the black protons? How many 3-bond neighbors do they have? Just 1, right? Because whenever we have symmetry, we just look at 1 proton in the set. And so we could say that black proton has 1 3-bond neighbor, so it will be split as a doublet. And what about the orange one? Also a doublet, right? They each have 1 3-bond neighbor because they split each other. All right, now the tricky part, chemical shift. I gave you guys a cheat sheet yesterday. And I'll give you this on the exams for second term, so you don't have to memorize these values. I just want you to know how to use the cheat sheet. But you can see a bunch of different functional groups. So for example, let's go up and look at our red protons. You see how our red protons are coming off of a methyl group? It's a CH bond. You could go down to our cheat sheet and say, well, CH bonds typically show up anywhere from 0.5 to 2-ish, right? So that's an approximate range you could expect to see those red protons. If you want to be even more precise, you can go in the Klein textbook at the end of the chapter, and he's got this predicting chemical shift table, right? And in this table, he says that methyl protons show up at 0.9 ppm. So he's being a lot more precise with his estimation. So let's go back up and put that into our table. Those red protons that I had labeled were CH3 groups or methyl groups. So they will show up at 0.9 ppm. So I'll put a little approximate 0.9. All right, let's look at the blue proton. Blue proton's still a CH, right? So let's go back down to this Klein table because his is a little bit more accurate. The blue protons are a CH. It's not a CH2. It's just a regular single proton coming off of a carbon. So we've got this base value of approximately 1.7. It's called a methine. However, let's go back up and look at it. For the blue protons, you guys notice that we have this carbonyl group right next to it? Those carbonyl groups are really electron withdrawing. So, do you think this will show up at a higher ppm or a lower ppm? Higher. It will be more downfield due to the inductive polling by that carbonyl group. And in fact, if you go to the Klein table, he says one easy trick is take this base value, which is 1.7. We know that we've got a carbonyl group next to it, so we're going to add 1 to this carbonyl group, right? So 1.7 plus 1.0 equals approximately 2.7, right? So that blue proton that we saw, we could estimate will show up at approximately 2.7 ppm. So let's go fill that in on our table. All right, what about the green protons? Well, we can go back to that Klein hint, and we can say, well, the green protons are CH2. So we'll go down, go down. I'm going to erase these for right now. Green proton, CH2. Is it next to a carbonyl group? Yeah, it's next to a carbonyl group. So what we do is we say, all right, 1.2 plus the 1.0 factor for a carbonyl group. That means that it's going to be about 3.2. And then did anybody else notice anything weird about those green protons in terms of their location? Let's go up. We said that the green protons are next to a carbonyl group, but what else are they next to? Aromatic ring. What do aromatic rings do? Yeah, the aromatic rings, like we saw yesterday, have an induced magnetic field that oftentimes causes shifting to a higher ppm. So what we would expect if we didn't have a benzene, that signal should show up at about 2.2, but the benzene will likely cause it to be bumped up probably another 1 ppm. So let's go back down to our math. What I would do is look at this and say this is due to the CO bond. And then I would say approximately 1 ppm more. And this is due to our benzene ring that is right next to it. So if anything, I would say this should probably be closer. Oh, I can't add. Why didn't anyone yell at me? 3.2. We would add 1.0 to the 2.2 and we would get a signal at approximately 3.2. So let's go back up and put that in our table. So a few people were asking me, are the effects additive? Meaning, if we have multiple electron withdrawing groups, do you add in those differences? Yeah, they can be additive and it will shift to a higher and higher ppm. All right, the black proton. Where will that show up at? Well, let's think about this black proton here. It's coming off of a benzene ring, right? If we go to the Klein table, none of these are coming off of benzene rings, right? So that doesn't really help us. But if you use my cheat sheet, we've got this AR. What does AR stand for? Aromatic. So these are protons coming off of an aromatic ring. And so the black proton and the orange proton are both coming off of aromatic rings, right? So they'll show up in a range of 6 to 9. People oftentimes come up to me and they say, that's a really big range. And I'm like, yeah, I know. Right? Aromatic protons don't always show up in a reliable location, and it's a little bit complicated because you're dealing with this induced magnetic field in combination with potential polar effects. So if we go up, it's okay to just write down, it'll be approximately 6 to 9 ppm for both of these peaks, right? So now we've got plenty of information to go off of. So let's take a look at our scale. Sorry, I know this is getting small. Our red proton should be a signal of 6 protons. It should be a doublet at about 0.9. So I'm just going to go through and very carefully draw in a big doublet at about 0.9, right? If I go to the blue protons, we should have a septet at approximately 2.7. So I'm going to draw this little itty-bitty septet. Sorry, I know it's not the greatest one. But it's a little hairy septet with 6 total peaks in there, right? Green protons, we have a singlet at approximately 3.2. So it's a 2H singlet, so I'll put it kind of at intermediate intensity. And then the green and the orange proton, we know that both of them are going to be between 6 and 9. So what I'll do is just put in 2 doublets somewhere in this range. This is a decent enough approximation for predicting the NMR, right? The key is don't overanalyze it and don't freak out if you can't get an exact value. You want to know a ballpark range for each of these values, right? Does that make sense? Yeah. This is supposed to be a learning process. I don't expect you guys to have been born knowing about NMR, right? Yep.
So we put like the doublet from 6 to 7 to 7 to 8. That's fine.
Yeah, the 2 doublets between 6 and 9 could be any location between 6 and 9. As long as you've got them ballpark identified, that's more than okay. All right, so In order to get good at these and the molecular formula, and I'm asking us to figure out the structure. So same kind of rules apply, we're just doing it in reverse and analyzing it the opposite way. There are some really useful tricks that I'll show you guys, so we'll work through this first one together. Before we do anything, let's determine the HDI for this molecule. So what do you guys think the HDI would be for this? It's going to be 1/2 2C plus 2 minus H. I'm not going to include the nitrogens and whatnot because we obviously don't have any. We only have carbons and hydrogens. So if we look at this, we've got 1/2. How many carbons? 2 times 6 is going to be 12. Plus 2 is 14. Minus 6 is 12. That gives us an HDI of 6. Or sorry, 4. Good. This is why I teach chemistry. So we've got an HDI of 4. What does that tell us?
There's 4 hydrogen. Oh, yeah.
There's either 4 pi bonds, or there's 3 pi bonds, 1 ring, or there's 2 pi bonds and 2 rings, or there's 1 pi bond and 3 rings, or there's just 4 rings. But we've got some clues already, right?
It's aromatic.
All right, what was that again?
Aromatic.
It's aromatic. If we look at the proton signal, it's showing up smack in the middle of an aromatic region, right? So if we think about the aromatic ring we're most familiar with, what is that called? Benzene. So let's draw in benzene and see if we're right. What's the molecular formula for benzene? C6H6, right? And it's got 3 doubles and 1 ring, so it fits with our HDI. If we draw in all of our protons, are these all equivalent? Yeah, it's got rotational symmetry. They're all in the exact same environment. So if we were to label these would all be HA. And what sort of splitting pattern would they have? They have no 3-bond neighbors because we said that equivalent protons can't split each other. So this has 0 3-bond neighbors, which means that it will split as a singlet, right? So if we look at this, this is a singlet for HA. Does that make sense? This requires a lot of brain power. It's like a puzzle on steroids, and these will get progressively more difficult. So let's do one last one together. We've got C3H8O. So let's do the HDI again. We've got 1/2 times 2 times 3, which is 6 carbons, plus 2 minus 8, which means we've got an HDI of 0. So we've got a good clue that there's no rings in this, and there's no pi bonds in it, right? All right, so now let's start analyzing the NMR. It looks like we've got what sort of peak around 4? It's a little hard to tell sometimes with these guys, but the key is if you look at that center peak, it's got to either be a pentet, meaning split into 5, or split into 7, right? Because it's unsymmetric. So we know it's either going to be a pentet or a sextet. So we've got to kind of piece together this. If it's a sextet, let's just assume it's a sextet, how many 3-bond neighbors should there be? So sextet is 7. What's septet? Right. So it has 6 3-bond neighbors potentially. All right. So let's kind of use our detective caps here and say this probably has 6 3-bond neighbors. What about this one around 2? Is that a singlet, doublet, triplet? Looks like a singlet to me. Okay. If it's a singlet, how many 3-bond neighbors does it have? 0. Has no 3-bond neighbors. All right, what about the peak right around 1? What is it? Yes, I am recording this. It's a doublet, right? So if we look at this one, it's a doublet. How many 3-bond neighbors should it have? Yeah. So it has 1 3-bond neighbor. Okay. So we've used our detective work. We can even analyze the chemical shift a little bit, but we know that this is in the range where it's not going to be an alkene, it's not going to be aromatic, it's not going to be an aldehyde, obviously, and it's not going to be a carboxylic acid. So it's probably going to be some combination of an alkane, right? So now what we can do, and oftentimes this is what chemists actually do, is they draw out the potential isomers. And then they try to look at those isomers and they say, which of these isomers fits the data? Okay, so we could say, all right, C3H8O could be propanol. Or what else? Okay, or isopropanol, right? So these are the 2 isomers. Which one do you think fits the data? So let's draw in the protons for isopropanol. Okay, if we look at the protons on isopropanol, I'm going to even change this last one to blue. We've got this HA proton on that alcohol. What about this one over here? It's its own, right? It's attached to a carbon that's attached to an alcohol that's attached to 2 methyl groups, so it's unique. What about these other methyl groups? So these are all going to be the same, these HCs. Is the other methyl group the same or different? Same, exactly. All right, so now if we look at HC, how many 3-bond neighbors are there? There's 1 3-bond neighbor, which means it should be split into what? A doublet, exactly. So we can immediately say, well, maybe this one, this doublet over here, corresponds to HC. What about this singlet here? What do you think that corresponds to? A. So we can say maybe this is HA. And then what about this last sextet? That could be HB, right? It has 6 3-bond neighbors, which means it's going to be split into a peak that's 7, right? So in this case, this is probably going to be HB. And if we look at our chemical shift chart, we know that HB is right attached to a carbon that's attached to an electron withdrawing group, which means it's going to be probably 2 to 4, right?
What about above the COH?
Which ones, HCs or?
No, the very top box on this carbon with an alcohol.
So that would be for HA. So HA, if we look at the carbon alcohol one, that's going to be anywhere from 1 to 6.
That's such a wide range.
Exactly. I'll talk about that in a second, but if we look at HB, we said that HB is attached to a carbon attached to an electron withdrawing group, so it should be about 2 to 4. If we look at HC, it's going to probably be in that 1 to 2 range, which is where it is. And then alcohols. Why do you think alcohols show up in such a wide range? H bonding, right? Hydrogen bonding screws with spectroscopy, right? Because it depends on how well it's hydrogen bonding with neighboring solvent molecules. So the reason it shows up in all these different areas is because it can have different hydrogen bonding neighbors, and it's a very unreliable peak. Anytime you have a peak that hydrogen bonds, it'll show up in a variety of different locations. It's not a good diagnostic tool. All right, so what I'm going to do is I'm going to let you guys work on the remainder of these problems in the set. I'll post the key online. It'll be in the course notebook. Also online, you'll be able to pull up a mass spec problem set, which I put up here, and then there's also an IR problem set. So if you just want practice working through these as like puzzle problems, you can go through those, and I'll post all the keys online. I also posted a second NMR problem set, so if you're flying through these and you're thinking these are really easy, can you throw me anything more challenging, you can work through problem set number 2, but it won't be representative of what will be on the quiz. Problem set number 2 is more challenging because I haven't given you any other spectral data. Normally, if I gave you something like this, I would give you a mass spec and an IR, kind of like you guys had on your lab handout. So try to work through these this weekend. I know a lot of you feel overwhelmed with how challenging this is, but the more you practice these, the more you kind of train your mind to pick up these clues really quickly. So I'll let you guys work on this, and then we'll go around the room. If you guys want to push tables together or work in groups, this is a really good activity to work with partners on. All right, one other thing I forgot to bring up that's also a very useful tool that the book uses is if you go to the Skill Builder review section, there's a section 16.3 where it says you can predict chemical shifts pretty accurately for some of these. So if you look at a regular methyl group where it's CH3, it's typically show up at a benchmark value of about 0.9. If you look at a methylene where it's CH2, these typically show up at a benchmark value of about 1.2. And then the methynes typically show up at a benchmark value of about 1.7. So we use these benchmark values, and then we can say, well, are there any polar groups nearby that might shift them more downfield? And so in this example, they say, all right, we're looking at a methylene group, which has a benchmark value of 1.2. And then this alcohol is going to shift at 2.5 ppm downfield. So we can very accurately predict that this should show up at 3.7. So how many of you guys finished problem 3? You guys get ethanol for that one?
Yeah.
Where did your quartet show up?
Like 3.75.
Yeah, 3.7, right? So this very accurately predicted where that methylene set of protons should show up for ethanol. Another really useful one is anticipating groups that are attached to esters. So if you look at an ester, you take that benchmark value, which is 1.2, and then add 3 to it. So it should show up at about 4.2. So if you are looking for esters, you can use this cheat sheet a little bit. And then if you're next to a regular ketone, instead of adding 3, you just add 1, because it's not as polar as being next to an oxygen on an ester. So you can use this as a guide too. It's the Skill Builder 16.3 for those of you looking it up. I'll give this to you guys, like I said, on the cheat sheet. But with the cheat sheet, I'm going to slowly wean you guys off of it. So there will be someday, at some point in time, probably later this term or early next term, where I'm like, no, you guys gotta get these down. All right. I'll know. Just to reiterate a point too, this X value here can be any electronegative group. It doesn't have to be a halogen. Oftentimes X's in organic chemistry mean halogens, but that can be any sort of electronegative atom. So that's one clue you can use too, especially if you're seeing peaks right around 3 to 4. They're probably next to a really electronegative group. All right, let's continue on and see how we can work through problems 3 through 12 on the in-class activity. If we look at problem 3, it's immediately clear that we've got 3 different sets of protons. We've got one proton set here, one proton set here, and one proton set here. Specifically, the one right around 4 ppm is a quartet, the one around 2.5 is a singlet, and the one around 1 ppm is a triplet. Another really useful trick when working through these problems is doing the HDI, or hydrogen deficiency index. And if you look at this molecule, it has an HDI that is equal to 0. So this indicates that there are no pi bonds and no rings in this molecule. If we're looking at the region around 3.5 to 4 ppm, we can see that there's a quartet. And if we go to our guidelines for trying to anticipate chemical shifts, we know that it should be close to an electronegative group. So let's go through it and try a few different isomers and see if we can see what we think might be going on. So one of the isomers could be dimethyl ether. The other isomer could be ethanol. So let's go through and see if one of these makes sense. Hopefully by now you can see that dimethyl ether is very symmetric. We should only have one signal for it, so we're probably not going to have this one. But let's take a look at the other one, the ethanol. If we look at ethanol, it's got protons on that terminal methyl group that are its own unique set, and it's got protons on the methylene that are its own unique set. So if we look at these methylene protons, they have three bond neighbors, which means that this will be split into a quartet. And then these methyl protons have two 3-bond neighbors, which means that they'll be split into a triplet. So what I'll do is I'll go through and I'll label these HA, and then I'll label these HB, and then I'll label this last one HC. So if we go back to our chart, we can see that we've got a quartet that corresponds to HB. It's next to an electron withdrawing oxygen, so it's a little bit more downfield. If we look at the singlet, that falls in the range for alcohols. They show up a little bit irregularly. They can be anywhere from about 1 to 5 ppm. So this is going to be HC, and then our triplet over there is going to be our HA proton. All right, so it looks like all of our data lines up. That means that this compound is most likely ethanol. All right, let's continue on and work on problem 4. If we look at problem 4, if we do the HDI for this problem, it's going to be equal to 1. That means we have either 1 pi bond or 1 ring, and then we've got a quartet, a triplet, and a singlet in here. In particular, if we look at this quartet, it's right around 4 ppm, which is very high for most protons. It means that it's either attached to a very electronegative group or potentially some sort of alkene, although if we have an alkene, it'd be much harder for it to form a quartet. So let's go through and try to figure out what this molecule is. One option would be to have some sort of carboxylic acid group in there. But if we had a carboxylic acid group, we would expect a peak from about 10 to 12 ppm. So we know it's probably not going to be some sort of carboxylic acid. Another option is that maybe we've got some sort of carbonyl group plus some sort of alcohol in there. In this case, that could be the case, although we don't really see a broad singlet, which is indicative of an alcohol. We do have a singlet over here. So let's try to work through this a little bit, but keep in mind that normally when we see alcohols, they tend to broaden out a little bit. They're not these really big, sharp peaks here. This really big peak here tends to be something that contains more protons than just one. The other option that I think would work well for this is some sort of ester. So if we look at esters and we go back to our correlation guideline, let me pull that up. Just one second. All right, sorry about that. So if we go and we look at an ester, we can see on this skill builder exercise 16.3 that the methylene carbons next to an ester should show up around 4.2, which in this case matches really closely with our observed chemical shift of about 4, a little bit above. So at this point, a lot of evidence is indicating that the compound that we're looking at in this NMR spectra is some sort of ester. All right, so now let's break this down a little bit further, and I'm going to put down 2 esters for this compound. I've got one ester here that corresponds to that same molecular formula, or I've got another ester over here. So I've got the methyl group on the right coming off of the oxygen rather than the left coming off of the carbonyl. So if we look at this, I'm going to go through and label these protons. So I'll call this HA. And I'll call this one HB. And I'll call this one HC. If we look at the protons for HC, they have no 3-bond neighbors, which could correspond to the singlet right around 2 ppm. And another good way of checking is these are protons attached to a carbon directly next to a ketone. So if we go back and we pull up our table, we can say, all right, where do they show up typically if we're next to a ketone? All right, we've got a methyl group on there, which has a benchmark value of about 0.9. And then it's right next to a carbonyl group, so we're going to add 1. So 0.9 plus 1 means that it's going to show up around 1.9. So let's go back and take a look at where it's showing up. In this case, it's showing up right at 2. Perfect. So that's a good indication that that methyl group could be next to a carbonyl group. Now let's take a look at HB over here. If we look at HB, it has 3 3-bond neighbors, which means it should be a quartet. And if we go back to our guide here, we can say, all right, if that's a methylene carbon, it means it has a benchmark value of 1.2. We take this 1.2 value and we add 3 to it. So if we do 1.2 plus 3, we get this value of 4.2 over here. So that quartet should show up somewhere around 4.2. Oop. And exactly, it's right over here. So we know that this is probably going to be HB. This singlet over here could be HC. And this one would be HA. Now, just for argument's sake, let's take a look at the molecule I have drawn right below. If we look at the molecule I have drawn right below, let's take a look at this methyl group. If we go back to our chart and we say, okay, this has 0 3-bond neighbors. If we did have this, it would be a singlet. And when we go to our correlation table, we can say, all right, if it's a singlet, it's a methylene peak right here. And it's right next to an ester. So we'd say 0.9 plus 3 wouldn't be 4.2, it would be 3.9 ppm. And if we go back to our in-class activity, we can see that our singlet isn't over in this region, it's actually over near 2. So we have evidence showing that it's not going to be this one. In fact, it's going to be the one on the top here. So let's erase this just so we're not confusing people. And let's go on to the next one. The next one, if we do the HDI for it, has a HDI of 1, meaning that it has 1 ring or 1 pi bond. And the tricky thing with this is we only have 1 signal here. So the question is, do we have a pi bond or do we have a ring? In this case, we've got 1 signal, which means that it has high elements of symmetry in there. And typically when I see very high elements of symmetry, I tend to think of things that are rings. So in this case, we could try to do a variety of different rings, but let's take a look at this particular ring. Oh. This is called 1,4-dioxane. And if we look at this, we have protons here, and over here, and over here. And the question is, are these all in the same or different chemical environments? Well, if you look at them, let's take this proton for example. The proton right next to it, coming off of the same carbon, is just in a different plane, but it's in the same chemical environment. So these are going to be the same. And then we also have a plane of symmetry going down the center of the molecule, which means the protons right below it are also in that same environment, meaning that they're right next to that oxygen too. They're just on the other side. So all of these are going to be HAs. And we know that protons that are equivalent can't split each other. So if we look at HAs, they have 0 3-bond neighbors, which means that it's going to split as a singlet, or in this case, not split at all. All right, so that one was a little tricky. Sometimes you have to go through a process of guess and checking. I know a lot of you were trying to do 4-membered rings with alcohols coming off, but if you do any of those, you would be getting more than one peak occurring in the NMR, and in this case, we only have one. All right, now let's do the next one. We've got another C4H8O, and if we do the HDI for this one, it's also going to be 1, so HDI equals 1. It has one ring or one pi bond. And one thing I'm noticing here is we've got peaks that are pretty upfield from a normal alkane peak. So there's got to be some sort of electron withdrawing group here. And again, this singlet peak here is pretty big. It's not very broad. It's probably not going to be an alcohol. So what I would do is, if it's not an alcohol, it could be some sort of ether, it could be some sort of ketone. We have to take a look at a lot of these. One thing it's not going to be is an aldehyde. An aldehyde would have a peak between 9 and 10 ppm. So in this case, it's probably going to be some sort of ether, or it could also be some sort of ketone. So let's take a look at some potential isomers and try to rule them out. Let's say we have, I don't know, some crazy looking ether. That would be C2. What if we have an ether like that? Well, if we had an ether like this, how many signals would we expect? Well, in fact, we would have a signal for HA. We would have another one for HB. HB, and then another one for HC. And then HD, HD, and then this methyl group over here will be HE. So we could try to make an ether here, but we would have 1, 2, 3, 4, 5 peaks. We're really only observing 3 signals. So we know that immediately we've kind of hit a dead end here. But we can try to do some sort of ketone. So let's try a ketone. So if it's a ketone and we start out like this, we only have 3 carbons, so let's add on another carbon on one end. And let's draw in our hydrogens. So we've got a methyl group over here, we've got a methylene, which is that CH2 peak over here, and we've got a methyl group here. If we look at the methyl group on the left, these are all the same because we know methyl groups can spin like helicopter blades. If we look at the methylene carbons, or protons, they'll be equivalent. And then the last methyl group will be equivalent. So this does have 3 signals, which is perfect. So let's take a look at these HA protons over here. How many 3-bond neighbors do they have? Well, they don't have any, so it should be a singlet. In this case, we could maybe say, well, maybe this HA is our singlet. If we go back to our NMR guide, we can say, all right, we've got a methyl group has a benchmark value of 0.9 ppm over here. It's right next to a carbonyl group. Let me erase all this stuff. So if we take 0.9 plus 1.0, it should show up around 1.9 ppm. So let's go back and check for in-class activity. Singlet's right above 2, so we're right on track. Now let's take a look at HB. HB has 3 3-bond neighbors, which means maybe this quartet belongs to it, and maybe the remaining ones, HC, belong to this last methyl group over on the end. But let's just double check. We said HB shifted around 2.5. We can go check with our sheet, and we could say, well, methylenes have a benchmark value of 1.2. If we go over here, 1.2 plus 1 equals 2.2. So it should have a chemical shift around 2.2 ppm. And it's right around 2.5, which is pretty darn close to where it should be. So this looks like great evidence for supporting this ketone that we have drawn here. All right, let's go to a more challenging one. All right, so if we do the HDI for this one, it gets a little bit crazy. I'll let you guys do the math, but what it should be is 5. So this has a lot of either rings or pi bonds or a combination of both. One thing that stands out immediately to me is we've got 2 peaks in the aromatic region. The only aromatic system we've seen so far in class is a benzene. So we immediately have a clue that there's some sort of benzene in there. And then we've got another peak at above 12 even. That's very indicative of some sort of carboxylic acid group. So while we do have a HDI of 5, we've already accounted for 3 pi bonds in the benzene ring plus a ring, so that's 4. And then the carbonyl group in the carboxylic acid would be 5. So this works out really well. Okay. Another thing to notice is we only have 2 peaks for our aromatic ring. If we only have 2 peaks, that means it's probably going to be symmetric, right? If we had groups coming off these positions, we wouldn't have 2 peaks, especially if we had R1 different from R2. If R1 was the same as R2, we could have 2 peaks. But typically we observe this sort of splitting when we've got R1 and R2 like that. It's a very common pattern. These are actually both doublets if you zoom on them quite a bit. So maybe this carboxylic acid is coming off of one of those positions. And then we've got to ask ourselves, all right, what are we missing? It looks like we're missing a carbon and an oxygen. So let's try to include those in. And the question is, would it be a carbon and then an OH? Or would it be this carboxylic acid where, ooh, that's a bad drawing, where one of these is a carboxylic acid and then the other end is some sort of ester. We've got to decide here. And what it comes down to a little bit is looking at the shift. If we look at this one on the left, we would have protons here and here, and then we'd have another set here, and then we would have a set here. So we'd have 1, 2, 3, 4, 5 signals in this NMR. This one we only have 4. So we know immediately it's probably not going to be that alcohol. We don't have enough signals to correspond to that. So let's take a look at this one over here. And in particular, let's try to label all of our protons. So I'm going to go through and label them as blue. So I'll label this HA. If we look down here, these are both HBs. These will be both HCs. And then I'll label these HDs. And let's see if we can assign these. So let's start with HA. We said that that's probably a carboxylic acid proton, so I'll label these HA. Then if we look at HB, it has 1 3-bond neighbor, so it should be a doublet. It's going to be one of these. I'm just going to arbitrarily assign it as that. We'll, if we have time, we'll cover how to predict where these are. And then this other one will be HC. We know that both of them are in the aromatic range. We don't know their relative position very easily. HD has 0 3-bond neighbors, so it's going to be probably this large singlet here. You can tell it has more protons since the area underneath it is much, much larger than, let's say, the signal for HA. So this integration area, the area under the peak for HD, is going to be 3 times the area under the peak for HA. All right, let's continue on. We've got C3H6O. This has an HDI of 1, meaning it has 1 ring or 1 pi bond. In this case, we could try doing both. Let's take a look at different ring systems. So if we have C3, we could have this as one isomer, right? Or we could have this as one isomer. Those are our possible ring systems. If we have a pi bond, we could have a few different options. We could have this. Oh, I'm missing one. So that's C3H6O. We could have something like this, or we could have one where there's a double bond between a carbon and an oxygen, kind of like that. Another one we could have just to be very thorough, would be to have some sort of aldehyde. So let's go through and look at these isomers and try to rule some out. So if we look at the ring one over here and try to predict how many signals it has, we can say, well, there's got to be a proton signals for these guys, right? That would be HA. Then we would have HB. And then this alcohol would be HC. There should be 3 signals for that, so it can't be this one. Let's do the next one. We should have HA, HA, and then HB, HB. So 2 signals. We only have 1, so we can rule that one out and say, well, it can't be that. The next one should have 3 signals, 1 for these methyl protons, 1 for the methylene protons, and then 1 for the aldehyde. We also don't have an aldehyde peak in the 9 to 10 range, so we know it can't be an aldehyde. It's not going to be this one. If we look at the next one, it will also have too many signals. We'll have 1 for this methyl group. We'll have 1 for this proton, 1 for that proton, and 1 for this alcohol. So we'd have 1, 2, 3, 4 signals. We only have 1, so it can't be that. Hopefully you're kind of seeing the pattern here. This one we would have a signal for this guy, signal for that guy, signal for that guy, signal for these protons, and then this alcohol. It's way too many protons. Last but not least, we can say, well, what about this compound? What about acetone? Are the protons on the left the same as the right? Yeah, because there's an internal plane of symmetry going down this molecule. All of these can be considered HA protons. So right now, immediately, we can say this is probably going to be acetone, not any of the other isomers we had drawn. So sometimes guessing and checking, especially with simple molecules, works very well. All right, let's do the next one. If we do the HDI calculation for C9H12, we get a HDI that equals 4. Another big thing we've noticed is we've got peaks in the aromatic region. This screams benzene ring, right? So we know it's probably a benzene ring with something coming off of it. In this case, the benzene peaks all in this aromatic region look like they're pretty clumped together. Usually when you see this splitting pattern, it means that either you've only got one substituent or you don't have very good symmetry. So in this case, we're missing 3 carbons coming off of it. So let's say we're maybe missing this guy. We could ask ourselves how many peaks that are non-aromatic, meaning they're not coming off of the benzene ring, should there be? Well, we'd have 2 protons here in a set. We'd have 2 protons here in a set. And we'd have 3 protons coming off the end. So it's probably not going to be that. We only have 2 other peaks that are non-aromatic, so it's going to be some other different configuration. Let's try this one, where we have an isopropyl group coming off. If we do this, we've got protons here. I'll call these HA. We've got protons here, and the question is, are these 2 methyl protons or methyl group protons the same? Yeah, they are, because we said an isopropyl group can spin around like a helicopter blade. There's an equal probability of them being in the same space. One thing people forget is that we have an additional proton here. So we'll call this HB. And then let's go through and label these. I'll label this HC and HD and HE. If you look at this proton down here, it's the same as HC. This one's the same as HD. So now let's analyze this, starting with HAs. So if we look at these HA sets over here and over here, they have 1 3-bond neighbor. So we've got 6 protons with 1 3-bond neighbor. That means it's going to be split as a doublet. So maybe this doublet down here is HA. Okay, that works. What about HB over here. HB has 6 3-bond neighbors, which means it's going to be split into a sextet. So maybe it's this guy over here. Additionally, we know that HB is on a carbon that's attached to an aromatic ring. So let's go back to the chart. Pull that up. One good trick to use is that these peaks that are carbons attached to aromatic rings typically show up around 2 to 3. So let's go back to our in-class activity. Yeah, it's right around 2 to 3, so that fits pretty well. And then we have to ask ourselves, well, what's going on in the aromatic region? So how many partners does 3-bond neighbors does HC have? 1. So HC should be a doublet. What about HD? HD gets a little trickier because it's being split by 2 different types of neighboring protons. It's being split by HC, which is a 3-bond neighbor, and it's being split by HE. So in this case, HD would be one of these weird examples of a doublet of doublets. Some people will say, well, it's got 3-bond neighbors, so it's triplet-like. I'd be fine with either of these. Oftentimes you can make out those doublet of doublets, other times you can't very easily. And then if we take a look at HE, it's got 2 3-bond neighbors, and these HDs, one 3-bond neighbor. And in this case, they're equivalent HDs, right? So if we think about this one, let me rephrase this and step back. These HDs, there are 2 of them in that position, so we can say that this one should be split as a triplet. So if we look at this one, it's a little confusing here, but what this is it's overlapping. It's an overlapping mess of signals that are HE, that triplet, HD, which is our doublet of doublets or our triplet-like doublet of doublets, and then our HC signal. So those are all overlapping there. This one I thought was pretty challenging. The key being is when you only have one substituent coming off of an aromatic ring, those remaining signals tend to clump together and overlap really well. Whereas if you look at our other example up here, when you've got substituents coming off of other positions, meaning not just one substituent coming off the ring, you tend to get much nicer looking splitting patterns. All right, let's do problem 10. Problem 10, if you do the HDI, HDI for this one should be 1. We only have one signal. That means it's highly symmetric. That makes me tend to think of rings. So if we think about this, we could do a ring that is 6 members. And if we did this, we'd have 12 protons. And the thing a lot of people have asked about is they said, well, cyclohexanes are in chair conformations, right? So if we draw our chair conformation like this, we know that we've got axial protons and equatorial protons, and those are not equivalent. At least if we freeze this in time, the axial protons are in a different space than the equatorial protons. The problem is the NMR doesn't take an instantaneous snapshot. It actually looks over a period of time, and this chair conformation can actually flip. So now if we look at these protons, one of them, actually let me do it this way, and I'll label these H axial is now in the equatorial position, and HB, which was equatorial, is now in the axial position. Cyclohexanes will flip-flop and do this inversion of a chair, or chair flip, and so over time they tend to average out and share the exact same signal. So if we look at cyclohexane and we look at it in the NMR, it's not locked into one conformation. It's actually rapidly flipping at room temperature, and so all of these protons are going to be equivalent because they're all going to average out over time. If we appended a tert-butyl group onto cyclohexane, then we could lock that tert-butyl group into the equatorial position, and we could actually resolve equatorial versus axial protons. But in this case, we're more concerned with the chair conformation. Let me actually leave this up here. I was going to erase it, and I'll just label this as fast inversion. So all of these are going to be HA. There are no HB protons because that HA and HB signal will average out. Alright, number 11 was pretty tricky, I thought. The last two I thought were more challenging than the others. This one has an HDI of 1, meaning there's some sort of double bond in it. Again, you can see the signal around 4, which anytime I see a quartet around 4, I tend to think of an ester. So let's just start by creating this skeleton that includes an ester, and then we have to figure out what's coming off this end on the right and this end on the left, and try to identify what substituents are coming off there. The other thing some people had trouble seeing was this little hump between 4 and 5. This strongly indicates that there's some sort of hydrogen bonding group going on there. Something that really likes to hydrogen bond, tends to broaden out really well. Peaks that do this are occasionally alcohols, or things like amides, phenols, things like that. In this case, it's showing up around 4 to 5. That's where alcohols, amines, and amides show up. Phenols don't typically show up in that region. So let me move this over. And this is one you may want to try guessing and checking on quite a bit. But one thing I have noticed is that this peak at 4 probably corresponds to protons coming off of here, just like we've already seen. And then there's a triplet over here, which is probably these terminal methyl groups. So oftentimes when I look at NMRs, I look for triplets and quartets. Triplets and quartets oftentimes are a good hint that there's some sort of ethyl group there. So I'll label these HA, and then HB. You know that this is HA, this one's HB. And then we've got these remaining two peaks over here and over here with this hump. If we look at our molecular formula, we're missing a nitrogen and we're missing a methyl group. So one functional group we haven't seen is this one. This functional group is called a carbamate. It's very commonly found in plastics like urethanes. It's a common functional group that we haven't really discussed yet. So if we look at this methyl group coming off the end, we could call this HC. HC has 0 3-bond neighbors because we can't go through that nitrogen. So if we look at that, this could be HC. And then if we look at this amide down here, this HD, that's going to hydrogen bond really well because it's an amide group over here. And amides are very electron withdrawing, means that this will be an excellent H-bond donor. Alright, so we can label this one as HD. So this one's pretty hard. Like I said, it's a new functional group called a carbamate. And this was meant to be one of the more challenging problems on the problem set today. Alright, the last one, if we look at it, it's got a HDI of 0. And in this case, we've got a peak really far upfield, actually in the region where we normally see aromatic protons, but we know that it can't be aromatic because we've got an HDI of 0. So in this case, we know it's going to probably be very symmetric, but it can't be a ring. So it's got to be some sort of linear molecule with a high degree of symmetry. So we've only got 3 carbons, that's our backbone, it's symmetric. Whatever's coming off of it needs to be the same on the right as on the left. And then we've got 6 chlorines coming off here. So let's take a look at a couple options. We could have 3 chlorines coming off of each end. And then we could have protons here. That would only be one signal, right? Because each of those protons is in one environment. Or we can say, well, what if there are some protons coming off the end, and then you've got 2 chlorines here, 2 chlorines here, and then chlorines here and here. We've got a decision to make. If we're looking at the protons of interest, they're going to be equivalent on the right and the left. But we've got to ask ourselves, which proton is more likely to be shifted all the way over into the aromatic-like region? And so we've got to ask ourselves, which one's bonded to the most polarized carbon? And in this one, you can see it's bonded to a carbon attached to 2 chlorines. In this one, it's attached to 2 trichloromethyl groups. And in this case, this one is actually more polarized than the one on the top, which means that this one is probably the better candidate for the NMR that we have drawn there. Although this is a pretty hard problem, and I'll say it won't be this one will be HA. So it's a pretty tricky problem. Those of you that were able to get through this will definitely do well on the exams and quizzes. If you struggled with this, don't be discouraged. Try to work through the sapling problems as much as possible. Do the problems from the book. The more you do this, the more you can see these tricks, like immediately identifying aromatic protons, quickly doing the HDI calculation, and so on. The other activities that I posted on the website and in the course notebook, I'll post the key to later today. All right, good luck studying, and let me know if you have any questions.